Hey there, students. Welcome to Psych 652 Lab, Module 4. Today we're going to be discussing statistical power. So today's lab's going to run a little bit different. I'm actually be just running through a slideshow with you all, and within that slideshow, I'm going to be first starting off by explaining kind of what statistical power is. I know Kevin explained a lot to you already in lecture, but I'm just going to kind of add on and not even necessarily add on, just reiterate some of the main points associated with it. And then we're going to actually learn how to calculate sample size from power and effect sizes via one of Dr. Murphy's articles. It's Appendix E. We'll learn how to calculate sample size with effect size and power. And then we're also going to be utilizing a program called G-Power. Now, if you haven't downloaded G-Power by this point, I'd advise you to go and download it right now because we'll be using it during the second part of the slide. So, this might be a relief to some people, but we will not be using R today. However, I do want to make it clear that this is all possible to do in R, and particularly in the Power package, PWR. If you have any interest in learning how to do it like that, please just don't hesitate to reach out to me. We can do a quick tutorial. I can even do it during lab if anyone desires that. Just let me know. But without further ado, let's go ahead and just continue on and talking about what is statistical power. So statistical power is really just this idea where we're trying to find the probability of finding an effect given there is an effect from our sample. So essentially, when someone says to you, I have a power of 0.80 in my study, it means that we have an 80% chance of detecting the effect in our sample given the effect is there. And generally, this is kind of equivalent to why p less than 0.05. It's kind of just like this one accepted thing among all of psychology, but we desire to have a power level of 0.80 or better. Usually anything under 0.80 as far as power goes is considered insufficiently powered. Additionally, we often are doing power analyses a priori, which means we're doing it before the start of the study so that we can determine what our sample size is. And this is an extremely important topic because if you're applying for some sort of grant and you want a lot of money for a research study that you really want to run, you're going to have to do a power analysis. It's likely this grant is going to want you to be sure that you're not wasting their money and that you have the sample size appropriate for running the study. So to determine sample size via power, we need three different things. We need to determine what our alpha value is, and that's the probability of getting a type 1 error. I'll explain type 1 error a little bit later as well, but as you know, we usually set our alpha at 0.05 in psychology. So generally it's 0.05. It might be 0.10, sometimes it might be 0.01 sometimes, but it's usually 0.05. We also want to have an effect size, which is usually determined from the literature. You usually get these from meta-analyses or something like that, or even from previous studies that we performed, we have a general idea of what the effect size is. And then additionally, we have our desired power. Usually we set our desired power to 0.80, but really it can be whatever you want it to be, 0.90, so you have a 90% chance of detecting an effect given it's there. It's really whatever you set it to and what's appropriate for your study. And I kind of wanted to go and just follow up more on kind of what an effect size. Sometimes I don't think it's very clear, especially, I teach this to undergrads, but I think it's also appropriate for graduate students to kind of be reiterated as to what an effect size is. What an effect size is really, it's the standardized difference between our groups, or it could be the proportion of variance explained depending on what type of effect size we're talking about. In the example of Cohen's d, which is one we'll be talking about, it's whatever the difference between the standardized difference between our two groups are while incorporating the variance between them. So take, for example, this image here. We have one value of a mean with a distribution associated with it. We have another value with a mean that has a distribution around it. And the effect size is that difference between those means while taking into account the variance between them and the variance that they share. Additionally, this can be determined by the percentage of variance explained. So we're going to be talking about R-squared values later. The odds ratio is also an effect size that we'll be talking about next week, actually. And then the other one we'll be using is called PV. And that's another one that's just kind of the proportion of variance that's explained from our study or whatever it is that we're doing. So we need to talk about the relationship between a few things. There's a relationship between effect size, your alpha value, sample size, study complexity, and power. And we're going to see how all these are related to power in particular. So as your effect size increases, so as those cohens D increases, power increases as well. So if you have a larger effect size for some sort of predictor and outcome or difference between groups, you have more power in your study. Additionally, as your alpha value increases, so does your power as well. So as if we were to move our alpha value from 0.05 to 0.10, we'd have more power within our study. However, we need to talk about the consequence of doing that. As you increase your alpha value, saying 10% chance of saying there is an effect when it does not exist, well, that's a really big shot onto your type 1 error as well. So you have to keep that in mind if you're going to increase your alpha value as a resort to increasing power. Usually, again, we set our alpha value to 0.05. Additionally, sample size is directly related to power. As our sample size increases, our power, our ability to detect an effect, also increases as well. And then lastly, we have to talk about study complexity. And when I talk about study complexity, I'm really talking about, when all things are equal, a study with 4 comparison groups or even like 4 predictors is going to have less power than a study with 3 comparison groups. So essentially, all things equal, so as the study complexity increases, as you have more groups or you have more predictors within your study, we have less power associated. So we need to build up on something like sample size or have a bigger effect size in order to have more power when we have larger complexity within our studies. So today we're going to be talking about 2 different methods for calculating sample sizes. The first is through Murphy, Myors, and Wolach's 2014 article in which they use Appendix E. And Appendix E is available for you in Canvas. At the end of this course, I'll show you how to get to it, but if you want to follow along with me, go to Canvas, go to the Module 4 lab, and download the Appendix E that's available there. Additionally, we're going to be learning how to calculate power via GPower, which is a downloadable power calculator program for Mac and Windows. It's completely free. And again, if you haven't downloaded it already, I would strongly suggest you download it. So let's go ahead and start with method 1 via Murphy, Myors, and Wolach's 2014 Appendix E. So really, what you can see here is that we have this appendix with all these numbers. It could look a little intimidating at first, but we're going to go ahead and really talk about the differences between here, and we're going to really dig into this, and it's going to be pretty simple once we talk about it. Now, the first thing that I'd like to note about this chart is that this table assumes that you've already set your alpha value to 0.05 and have a power value of 0.80. So again, that's 5% chance of getting a type 1 error and an 80% chance that you'll detect the effect given that the effect is there. So really, you're making that assumption. And it's not a bad assumption to make because most studies that we run have these values already set for us. But just keep that in mind when we're running this. When we get to GPower later, we're going to learn that we can adjust those settings within this. We can adjust our alpha values and our power level as well. But really, within this chart, there's 3 main components we need to look at. The first is highlighted in red up top here, which is the degrees of freedom hypothesis. And all this is really is just the number of groups or number of predictors you have minus 1. And again, then there's the orange here on the left side, which is our effect size. This is essentially saying, well, how much percentage of explained variance do you have? Or how large of a standardized difference is there between their groups? And then lastly, highlighted in green here, the large box in the middle is the degrees of freedom error. And essentially, we use the degrees of freedom hypothesis and our effect size to determine what the degrees of freedom error are. Then we use the degrees of freedom error to calculate our sample size, and that's the end product. So I kind of already explained this to you, but this is just a better defining definition of what these are. So again, degrees of freedom is an index of complexity of the problem. So for example, if we have 2 groups, with our degrees of freedom hypothesis is 1. When we have 5 groups, our degrees of freedom hypothesis is 4. If we're evaluating 7 predictors of an outcome variable, our degrees of freedom hypothesis is 6. So you're noticing the trend. It's just however many groups or predictors you have minus 1. The effect size is either the proportion of variance explained or the standardized difference between your groups. So proportion of variance explained is that PV value. So 0.20 essentially means that there's a 20% of the variance is explained. Additionally, a Cohen's d of 0.2 saying there's 0.2 standard deviations between our groups. And if you remember back to that chart earlier, we're just showing that there's two differences between these groups. And then next we have the degrees of freedom error, which is the estimate of the error used in the test. And again, we use our degrees of freedom hypotheses and the effect size to determine our degrees of freedom error. And once we get our degrees of freedom error, we can calculate the sample size. And y'all, that's the end product of it. So we want to know what our sample size is. So keep that in mind. Once you've reached the sample size, you've used this chart correctly. And all that the sample size is the degrees of freedom hypothesis plus the degrees of freedom error plus 1. And we have to add that plus 1 because we removed it earlier from the degrees of freedom hypothesis. So let's go ahead and just use an example. I'm going to use this as like word problems, and I'm going to hope that you can kind of follow along with me with this. Well, maybe you can have your table open up at the same time and be kind of charting it with me and seeing if you reach the same conclusions that I do. Oh, well, actually, I forgot. So we're going to be using Appendix E to get our sample size essentially, but there's 4 essential steps that we're going to be doing. So our first step is to identify the degrees of freedom hypothesis. Then it's to determine your effect size, which is normally found in the literature. Here we're just going to be telling you. Then you determine the degrees of freedom error using your degrees of freedom hypothesis and effect size, and then we calculate the sample size. So now should be where my word problem comes in. Yes, so let's go ahead and just do an example here. So you're conducting a study that has 2 groups in it, an experimental and a control group. And recently, a meta-analytical review has recently shown that the effect size is shown to be a PV of 0.10. So now we have to ask the question, how many participants are needed to reach desired power of 0.80 with an alpha value of 0.05? So what I'm going to go ahead and do is highlight the important variables of interest here. What are the numbers that we're interested in here? All right, so we got us in red. We have 2 groups. That would match our degrees of freedom hypothesis, and we know that the effect size is 0.10. And we know that from this table, that we need 0.80 and 0.05. So now we need to go ahead and identify what our degrees of freedom error is given this information. So if you go ahead and you pull up your Appendix E, we can go ahead and map it out. So step 1 is identify our degrees of freedom error. So we have 1 for our degrees of freedom error because we have 2 groups and it's your groups minus 1. So right here 1 in red. Then we remember what our PV is. Remember our PV was 0.10. So we go down and we say, okay, our PV of 0.10. From here, we see where those 2 lines meet. So we go down there and we see where they meet, and it meets at 73. So in order to get our sample size, it's simple addition from here on out. We get our degrees of freedom hypothesis, which is 1, plus our degrees of freedom error, which is 73, plus 1, which equals out to 75. So what we've essentially found is that in order to have a power of 0.80 at an alpha value of 0.05, we need 75 participants to participate in our study with us. So really, as you can see, it's not too complicated to use this table. It's actually quite quick and efficient to use it. And that's why we're teaching it to you, because it's a quick and efficient way to find your power. So let's do another example. So you're running an observational study, and for your analysis, you plan to use 7 variables to predict an outcome. So remember, this is observational. We're not talking about groups. We're using predictor variables. Your advisor tells you that the general effect size for the predictors of interest and the outcome is PV equals 0.23. So we got to ask ourselves again, how many participants are needed to reach a power of 0.80 with an alpha value of 0.05? So let's go over our steps again. So we have 7 variables. We have identified our degrees of freedom hypothesis, which is 7 minus 1, so we have 6. And then we identify our effect size, which is 0.23. All right, so then we go and we take those 2 things and we identify what our degrees of freedom error is from the Appendix E table. So from this Appendix E table, we determined that our degrees of freedom hypothesis is 6. We determined that our effect size is 0.22. So we go ahead and scroll it over and see where those two meet, and it's at 54. So we got to take our degrees of freedom hypothesis, which is 6, add in our degrees of freedom error that we determined, 54, and then we add 1. So simple addition says 6 plus 54 plus 1 is 61. So really, we need 61 participants to reach a power level of 0.80. So again, that's an 80% chance of detecting that effect size of 0.22. That's what we're looking for. So we need 61 participants in our study. So if we were to write a grant, we'd say we conducted a power analysis via Murphy and Wolach and determined that we needed 61 participants to reach a power level of 0.80. And that's all that there is really to that. And you can go ahead and on my assignment that I'm going to provide to you today, I give you a few more examples, and you can try and practice on your own as well. So now we're going to go ahead and focus on method 2, which is G-Power. And another reminder, make sure you have this downloaded by now. It's going to show up and it's going to look like this over here. It's a pretty simple calculator, but it has tons of, well, power, like we're going to be talking about today. But it's really useful and a really handy tool to have. So let's go on. So what is G-Power? G-Power is this great power calculator. It allows you to calculate the sample size if you give it power and alpha value and effect size. And we can also go backtrack and we can calculate power of a study given the sample size, the alpha value, and the effect size. And to be honest, there's a lot more capabilities to this G-Power calculator than I'm going to be providing you today. I'm going to be giving you kind of the bare minimum of what you should know from G-Power calculator. But if you have other studies running in the future, G-Power is probably going to be pretty great for you. And you're going to be able to say, you're going to have to kind of do some more research on your own, but you'll probably be able to find a power analysis that works for your study because every kind of analysis requires its own type of power analysis. But with G-Power, it allows you to do all those different power analysis. So today, we're just going to be discussing t-test and ANOVA power analyses. The rest you're going to be kind of figuring out on your own as you proceed on with your research careers. So there's two terms that I want to discuss with you first. So the first one is a priori. So whenever we're running a study, we want to try and do a power analysis before we run the study to determine the sample size. However, sometimes we end up running them post-hoc as well. So post-hoc is when you run the power analysis after the study to determine how much power the study had. So you already have a sample size. You're just curious as to, honestly, you may not have found a significant effect. So you're kind of sitting there like, uh-oh, maybe I didn't have enough power or something like that. We'll see. Hard to say. So in reality, we can say that a priori analyses are preferred, but sometimes the only option we have is a post-hoc analysis. And so we're giving you the ability to run that today, And we're going to teach you how to run that today as well. So let's go ahead and just talk about what this G-Power calculator is. And we're going to split it up into different components here. So in blue here, you have your statistical model. So if you're on your calculator right now, you'll see there's a test family and you can click on that. There's an F-test, there's a chi-square test, there's all sorts of different tests on there. We're going to be focusing on the t-test and the F-test today. And then, depending on what your test family is, there's going to be different statistical tests that show up in here. There's going to be independent means comparison. There's going to be four groups comparisons. There's going to be all sorts of comparisons that we could do. Or a correlation model, even if you want to. There's all sorts of different things. We're going to be focusing on two different ones, and we're going to be focusing on them a priori and post-hoc. And the type of power analysis in green here is essentially where you determine whether you want to do a power analysis a priori or post-hoc. There's also a couple other options that you can fiddle with later. And then here's our inputs. Our inputs are going to change based on what everything up here was set to. So depending on what it is, right now it's set up for a t-test, correlation, a priori. But we're going to be manipulating these so that down here will change. And then over here on the right in orange is your outputs. And that's essentially going to be the answer to your question always. And really what we're either going to be focusing on is the power or whatever the sample size is. And that's what is going to be the essential answer to all of your questions and power questions, whether you had enough power or what sample size you do need to achieve a power of 0.80. So let's go ahead and get started. So I went ahead and just created another word problem for you all to run. So here's how it goes. It says, your planned study is a randomized controlled treatment assessing the mean differences of sexual knowledge scores between participants that took a 12-week sexual education class versus those in a control group. And the control group was just those with no classes. An independent samples t-test will be used to assess the difference. So you want to use an alpha value of 0.05 because that's pretty standard. And a recent meta-analysis that came out has shown that sexual education classes generally show an effect size of about 0.12. So we're going to ask the question, what sample size would be needed to achieve a power level of 0.80? So the way that I like to do this again is I just highlight everything that we need from this word problem. And again, you're not dealing with word problems, but you have to think in this logical way of like when you get a study, you say, okay, what type of test am I running? What's my alpha value? What has past research shown about my field of study? And what do I want my power level to be? So of course, word problems aren't the way that we do it in real life, but these are just kind of essentially showing you the components. So we first say, okay, so we have an independent samples t-test. That's a type of test we're going to be running. Our alpha value is 0.05. Our effect size is 0.12, and we want to achieve a power level of 0.80, which is pretty standard. So in this next slide here, I went ahead and entered in all of the options that we need in order to do this. So if you're working on G-Power right now, try to get it so that your G-Power matches everything up here. So we start off, we want it as a t-test. And the statistical test we're looking at is the mean differences between two independent groups. Because again, it's an independent samples t-test. When you think about what a t-test is it's just comparing the two means of different groups. And we did this before we ran our study, so it's an a priori analysis. And we always set our tails to 2, unless for some reason you have reason to believe that this is a one-sided test or something like that. But most of the time, I'm going to say you're probably going to want a 2-tailed test for this study. And so we determined our effect size D is 0.12. We have an alpha value set at 0.05 and a power level of 0.80 or 0.8. And this allocation ratio, you're not going to change really unless you have reason to believe that your group sizes are going to be different. But you go ahead and you do that, and on the bottom right of it, I think my face is actually covering it right now, is a button that says calculate. If you have all your inputs put in like that and you press calculate, you should get a numbers that look exactly like this. So we don't really need to worry about the non-centrality parameter. The critical t is essentially the t that you need to find to determine a significant effect. The degrees of freedom is essentially just your degrees of freedom, and then what the sample sizes would be for each of these. These will stay the same unless you change this allocation ratio. And then our total sample size of 2,184, and that's the answer we're looking for. So we're saying we need 2,184 participants to have an 80% chance of detecting this effect size of 0.12. So again, it doesn't guarantee you're going to get it, but it's saying you have an 80% chance. And for some reason, us in psychology, we're okay with an 80% chance of detecting the effect, just like we're okay with having a 5% chance of committing a type 1 error. So that's really all you need to do for that. And if you're having questions with this, please feel free to email me, talk to me during lab, and we can talk it over a little bit more. So again, the total sample needed is 2,184 for a desired power of 0.80. So again, that's an 80% chance of detecting the effect size of 0.12. So let's do another one. Now we're going to be doing this through an omnibus ANOVA. So let's say you're focused on creating a study with 3 groups, trying to see if different yoga interventions have an effect on eating habits in college students. So the plan is to conduct a one-way ANOVA, and generally the expected effect size for interventions like these on eating habits is 0.15. So using an alpha value of 0.05, what sample size would be needed to obtain a power level of 0.80? So again, go ahead and just highlight all of our terms. So we have three groups. It's a one-way ANOVA. We have an effect size of 0.15. Our alpha value is set to 0.05, and our obtained power that we're looking for is 0.80. So we go ahead and get to G power again. This time we change our test family to an F test because with ANOVAs, it's always an F test that you're utilizing. And the statistical test we're using is going to be an ANOVA fixed effects omnibus one-way ANOVA. So we're just looking at a generalized model here of an ANOVA. And if you're really interested in regression outputs or specific types of ANOVAs, it has all those too, but we're keeping it with kind of the bare bones basics here. And then we're going to say what type of power analysis are we trying to run? Well, again, it's an A priori. We haven't run the power analysis. We haven't run the study yet. So we set this to A priori. So our effect size is 0.15. We have our alpha value set at 0.05. Our power level is 0.80. And then we also have to indicate the number of groups. Remember, this is the actual number of groups. This isn't the degrees of freedom hypothesis anymore, so we're not subtracting one from anything. It does all the work for us, actually. So we have three groups in our model. And then again, on the bottom right, you press calculate. And once you press calculate, you should get an output that looks exactly like this. So again, we have that non-centrality parameter that we're not going to worry about. We have the critical F, which is the F you need to obtain in order to obtain a significant effect. We have our degrees of freedom numerator, which is really just the number of groups minus 1. We have our degrees of freedom denominator. And then we have our total sample size, which again is the exact answer that we're looking for. So we need 432 participants in order to participate in the study to have a power level of 0.80. So again, 432 participants to have an 80% chance of detecting an effect size of 0.15. And I think it's very clear. You notice how I emphasize that it's an 80% chance. It's not guaranteed you're going to get that effect. You're going to detect that effect, but it's really good. There's 20% chance you won't detect it, but we're okay with an 80% chance of detecting it. So now we're going to try and do a post hoc example. So let's go ahead and do this, and this is going to be with the t-test again. So you recently ran an experimental study and failed to find significance between the control and treatment group when alpha was set at 0.01. Notice how we have a different alpha now. This completed study yielded an effect size of 0.25 between the two groups. You use an independent samples t-test to do this, and your sample had 200 participants in each group, so it's 400 in total. So what was the power of your study? So really, you'd think, wow, 400 participants, that's a lot. That seems like it would really work out really well for us. But it seems like we didn't find an effect, so we're going to determine, did we have enough power or what? So let's go ahead and we're going to highlight all the things that are important to us. So we have our alpha value set at 0.01. We have an effect size of 0.25. We're running an independent samples t-test. And we have 200 participants in each group for a total of 400. And we're going to try and determine what the power of our study was. So we go ahead and input our parameters. So things are going to look a little different now. Well, as far as test family and statistical tests, it actually looks exactly the same. So we did a t-test. We're comparing the difference between two independent means. And then we change our type of power analysis to a post hoc analysis where we're trying to compute an achieved power given alpha, sample size, and an effect size. And again, we keep our tails at 2. It's more than likely that we're going to keep this at 2 unless you have a direction effect that's very clear. I'm going to say it's not very often that happens, but generally we are interested in it in a two-tail test. We have our effect size set at 0.25, which is a moderate effect size, honestly. That's a pretty good one. Our alpha level at 0.01, that may have been something that really hit us, is that we lowered our alpha value so hard that it makes it hard to detect an effect. And additionally, we set the sample sizes for each of our groups, so it's 200 in each. It's looking to see if there's differences between groups' sample sizes as well, which could affect power as well. I didn't mention it, but if you have different sample sizes between your groups, that can affect power as well because you have to use a pooled sample, and it's a little bit more complicated. But we go ahead and we press calculate, and then over on the right we get our output parameters. we get our critical t. So we need a t of 2.588 in order to have achieved a significant effect. Our degrees of freedom is 398. So that's just your sample minus 2. And then our power, which is the answer we're looking for in a post-hoc analysis, was 0.465. So in reality, we only had a 46.5% chance of detecting any effect given that was there. So even with kind of a moderate sized effect size, but our alpha value was set so low, it made it really hard for us to detect an effect. So really, we only had 46.5% chance of detecting an effect that was there. So really, we are less than half ability to detect an effect. So it was pretty low. So really, if you ran the study, and you're probably hitting yourself on the head right now, being like, oh my gosh, I didn't even give myself a chance to detect an effect. There's no point of even running the study. And that's why they won't allow you to run studies without a power analysis if you're applying for a grant. So these are extremely important. So I got one more. This is the longest one, but don't worry. We're going to get through it. So I'm going to go ahead and read it off. So it says your friend conducted a study to compare the impact of 5 yoga workouts. They recruited a sample of 250 undergraduate students. So that means that 50 participants were assigned to each group. And of these 50 participants, they were each assigned to one of the workouts. They only did one of the workouts. They didn't cross anything. And they were asked to self-rate their mood after their workout. So after your friend collected all the data, they conducted a one-way ANOVA to compare the mean mood ratings across the 5 types of yoga workouts. So at a significance threshold at alpha equals 0.05, the results were non-significant. So they're sitting there like, oh no, right? So previous literature indicates that the effect size for the mean difference across the food groups should be around F equals 0.1. So we're going to ask, was their study sufficiently powered to detect an effect of 0.1 if it exists across the 4 groups? So again, I'm going to go ahead and highlight the important numbers here. So we have 5 groups, 250 undergraduate students with 50 in each group, an alpha value of 0.05. We are also conducting a one-way ANOVA, and our effect size is 0.1. So we're going to go ahead and plug all of those in as well. So we go to our test family, which is an F test. The statistical test is an ANOVA, fixed effects omnibus one way. And we're doing a post hoc analysis here. So we're giving it an alpha, a sample size, and effect size to get what our power was. Then we fill in these components in our input parameters. So our effect size is 0.1. Our alpha value is 0.05. We had 250 participants in our sample, and there were 5 groups. And that's something that really might be adding to the complexity here, is that there's 5 groups. Remember, study complexity makes it harder to have power. It lowers your power every time you add a group. So we go ahead and look at our critical F. So they needed an F value of 2.408 in order to have achieved a significant effect. Our numerator's degrees of freedom is 4. Our denominator degrees of freedom is 245. And our answer to this question is we had a power level of 0.2037. So what that means is we only had a 20.4% chance of detecting the effect. So that was even lower than our study. Your friend did not do such a hot job on this. They did not. They would have done a power analysis beforehand. They would have found out, oh my gosh, I need to recruit so many more participants. So unfortunately, they're kind of out of luck at this point. They say, oh, well, I guess I'm just going to have to hedge my bets and have to do something else now. So this was an extremely underpowered study. So in conclusion, again, power is the probability yield to detect an effect given that the effect is there. So I know I've been using 0.8 this whole time. I'm going to switch it up and say a power level of 0.7 means you have a 70% chance of detecting the effect. Power analysis are essential to any study. Please, before you do a study, do a power analysis. It's so essential. Determine what your group size is going to be. It's really people not doing proper power analysis in the past, as you read in your readings, has kind of led to a lot of big problems, especially with when we're doing this hypothesis testing and nil and null hypothesis testing. And again, so effect size, alpha values, sample size, and even study complexity drive how much power you have. So in this lecture, we learned two methods to calculating power. The first is the Murphy, Myers, and Wolach Appendix E. The second is through G power. So now I'm going to go ahead and tell you to start doing your assignment on Canvas. And I'm going to go ahead and, if you want to, I'll show you how to get to the assignment, and then we'll go ahead and do the assignment together. I'll do two problems with you, one via Murphy, Myers, and Wolach, and the other one via G-Power. If you don't want to do it with me, then that's fine. You can go ahead and pause this video, and then we'll be good. So go ahead and exit out here. So thanks again for listening to the lecture, but let's go ahead and go to Canvas and see if we can get the appropriate stuff for our homework assignment. So we're on Canvas. We're going to go to Modules, and then we're going to go to Module 4, Lab. So on here, I have the G-Power download page, I have the Appendix E, and I have the Module 4 Activity Lab, and then also the turn in the activity here. So let's go ahead and first download the activity. So go ahead and download it. It's going to be a .docx. If anyone has a problem with that and they need a PDF form, please don't hesitate to let me know. Okay, and I'm going to go ahead and pull it over here. All right, enable editing. We're going to go and zoom in. So what I do here is I give you kind of your definitions again. And the first part of this is that I want you to use Murphy, Myers, and Wolach's 2014 Appendix E to compute the sample sizes for the following problems at a power level of 0.80 and an alpha value of 0.05. So remember, this power uses two alternate ways of indexing power via D and PV, or the percentage of variance explained. So in general, a PV of 0.01 or 0.10 and 0.25 represent small, moderate, and large effect sizes, respectively. So let's go ahead and just work on problem number 1. So it says, for a study comparing two groups, calculate the degrees of freedom error and sample size required to detect a PV of 0.01. So we know that we need to go back to our Canvas page. Let's go ahead and go back. And we're going to download this Murphy, get back to it, this Murphy, Myers, and Wolach Appendix E. And we're going to go ahead and click on that. Download that, and that will load it up in another screen, and I'll get it over here. So let's go ahead and first determine what we need. So we have two groups. We need the EF error, and our PV is 0.01. So if we go to our table, we'll remember that our DF hypothesis is the number of groups minus 1, so that's 1. And our effect size is to the left of 0.01, so we have 1.01. We go over, our DF error is 775. So DF error equals 775. But what we really want is we also want to calculate the sample size. So remember, sample size equals DF error, which is 775, plus our DF hypothesis, which is 1 plus 1. So really, our sample size equals 777. So the answer to our first question is 775 for the DF error and 777 for the sample size. So go ahead and try to answer number B and C by yourself. See if you can understand it. If you're having troubles, please feel free to contact me. And then we're also going to go down to this method 2, in which we use G-Power to perform an a priori compromise post hoc analysis. And again, here's the link. So let's go ahead and run over this word problem here. So your advisor has recently found out themselves in a busy mess and they don't have time to run a power analysis. So they have a grant that's due tonight. So because you're an ambitious grad student, you take on the task. So the study is a randomized controlled treatment assessing the mean differences of anxiety scores between participants that took a 12-week mindfulness meditation class versus those in a control group. So an independent samples t-test was performed. So I'm going to go ahead and highlight that. will be used to assess the difference, and you're instructed to use an alpha value of 0.05. So I'm going to go ahead and highlight that as well. And a recent meta-analysis that came out has shown that mindfulness interventions in anxiety tend to show an effect size of 0.30. So that's a pretty big effect size in this imaginary world that we created. So what would the sample size would be needed to achieve a power level of 0.80? All right, so what I'm going to do is I'm going to go ahead and go to my G-Power first. So I'm going to go here, and then on my desktop, I have G-Power. Might be in your applications if you're a Mac user, or it might be in your Start window here. So I'm going to go ahead and just have my Word document open at the same time as this. So we have our G-Power open. So I'll put it right, I don't know where to put it. The best place to put it, we'll put it right over here. Okay, so we go ahead. We know that we're performing a t-test, so that's correct. Our statistical test is going to be a means difference, independent means between two groups. It's not a matched pairs, so a mean difference between two groups. We know that this is a priori because we haven't done this study yet. We're going to set our tails to 2. Our effect size is 0.30, so 0.30. Our alpha value is 0.05. We're wanting a power level of 0.80, and we're going to keep our allocations the same. So we go and we say, okay, we have everything correctly set on here, and we go ahead and we press calculate, and it gives us our fancy chart that looks really nice. We have a critical T. We need a critical T of 1.96 in order to get a significant effect. Our degrees of freedom is 350, and our groups would be 176 each, and we need a total of 352 participants. So we need a sample size of 352 to have an 80% chance to detect an effect size of 0.30. That's your answer. You need 352 participants to have an 80% chance to detect an effect size of 0.30. So I think you can figure out the rest on your own. I have some questions. I have some conceptual questions too. Don't worry too much if you're a little lost in the conceptual questions. I just wanted to challenge you a little. Just try your best to answer them. If you're really struggling, you can come to me. But really, I think you are a lot better at answering those than you think. And then, yeah, so go ahead and go through that and be sure and let me know if you have any questions. And that concludes today's lecture. Thank you so much.